Namaskaram. In this session, we will discuss the simplest algorithm for solving a linear programming problem. Okay, we know that this is the general form of LPP and this is the matrix notation of LPP. Also, we have seen that if number of variables is 2, then we can solve an LPP using graphical method. Okay, so number of variables is greater than 2, we cannot use a graphical method. So there is an algorithm that is called simplex algorithm. So applying simplex algorithm, first we have to convert given LPP in a standard form. So what is the standard form of an LPP? Okay, the first step is we have to convert all the constraints in an equations. Okay, by adding slack or surplus variables. That means suppose we have two equations like this, x1 minus 2x2 less than or equal to 7 and 3x1 plus x2 less than or equal to 5. So first you have to convert these two equations, these two constraints as equations by adding slack or surplus. Slack means suppose in the first equation actually this LHS is less than 7. Okay, so to make an equation we have to add something on the left side. That means what? We can convert this is like this, x1 minus 2x2 plus something plus some s1 equal to 7 because LHS quantity is less than 7. So by adding something that is equal to 7. And what about the second equation? Second equation is 3x1 plus x2. Oh, sorry, suppose equation is like this, greater than or equal to. Okay, then in this case the left hand side is greater than 5. So we can make this as an equation by subtracting something. Clear? So this is greater than 5. So by s2 is equal to 5. So this variable is called slack variable and this type of variables are called surplus variable. Clear? Okay, second step is the RHS of each constraint should be non-negative. Okay, so for example, you consider another equation, another constraint like this. Okay, suppose a constraint is like this, 2x1 minus x2 plus 4x3 less than or equal to minus 5. So actually here LHS is less than minus 5. So you can make this inequation by equation either by adding a slack variable, like for example s3. If you add this plus s3, it is clear that this is an equation like equal to minus 5. But this is not allowed in our standard form of LPP. In our standard form of LPP, RHS is always non-negative. So how to make this as an equation with the RHS is positive. So first you multiply whole inequation with a minus sign. So what happened? Minus 2x1 plus x1 minus 4x3 is greater than or equal to 5. Now here LHS is greater than 5. So we know we have to subtract a surplus variable. Okay. Yes, so this minus something equal to 5. So this S3 is surplus, not slack. Okay, so this is not allowed in our standard form of LPP. Okay, next one is objective function should be in maximization type. Okay, we know that there are two type of objective function in LPP, either maximization or minimization. So in our standard form, minimization is not allowed, only maximization type. So suppose there is a LPP with a minimization problem, then we can easily convert that minimization problem to maximization problem using this idea. Minimum of z, we can convert minimization of z to maximization of minus z. Why? Okay, for example, suppose this is our value of the function z with respect to some variables. Okay, whatever be. So actually we have to find so problem is to find the minimum of this function. So that means we have to identify this point and this value, that is the minimum value of this function is. Okay. So but we have to convert this problem into, so actual problem is minimum of z. Okay. So we have to convert this problem to maximization type. So you think about minus z. What is minus z? Negative of z. So that is a reflection about the plane almost like this. So this is our function minus z. Okay. Then what about this point with respect to minus z? In the case of z, this point is minimum. Then in the case of minus z, this point is maximum. Clear? So this value is less than this quantities. So this point is actually that is given by the maximum of minus z. Okay. So maximum of minus z obtained at this point. Then actually what about this maximum of minus z? That is this height. Okay, we have to find this height. So what is the relation? You simply take the negative. So minimum of z is equal to minus of maximum of minus z. Anyway, this is the reason behind this conversion. So if our problem is minimization type, then you can convert the problem as maximization type by taking maximum of minus z. And ultimately the minimum is given by this equation, minus of maximum of z star means minus z. Okay. Okay, another procedure in standard form is if xi is unrestricted in sign. That means we know that in our LPP all the decision variables, that is all the x1, x2, all the decision variables are non-negative. Okay, but in some situations there is no restriction for some variables. That is called that is unrestricted in sign. Unrestricted in sign means there is no restriction in sign. That means suppose x1 is unrestricted. That means x1 can take positive, negative, 0, whatever be no problem. Okay, but in standard form this is not allowed. In our standard form all the decision variables are, or all the variables are non-negative. Okay, so suppose one variable is unrestricted. Suppose x1 is unrestricted. If xi is unrestricted in sign, then we are going to replace xi by xi dash minus xi double dash, and also we assume that these two variables are non-negative. That is possible. For example, x1 is unrestricted. That means x1 can take any number in between minus infinity and plus infinity. Then we are going to substitute instead of x1 dash minus x1 double dash. Okay, so what is the meaning? And we assume that x1 dash comma x1 double dash both are positive. This is possible because whatever be the number, we can convert that number in terms of difference of two positive numbers. For example, x1 equal to 10. Then you can write this as some 15 minus 5. That is possible. Both are positive. Okay, suppose x1 equal to some minus 7. Okay, then you can write this minus 7 as difference of two positive numbers, isn't it? Yes, for example, you consider 2 minus 9. Here 2 is positive, 9 is positive. So you can write this minus 7 as difference of two positive numbers. Okay, so in this case, this is our x1 dash, this is our x1 double dash. Okay, so this is possible for every number, whatever be positive or negative, whatever be, always we can convert a number into difference of two positive numbers. That is the idea behind this conversion. So anyway, if some decision variables are unrestricted, then we will convert that variable into like this. If xi is unrestricted, then we have to convert all the xi's by xi dash minus xi double dash. Okay, and we can assume that they are positive, non-negative. Okay, so this is the process of converting a given LPP to a standard form. Next one, we consider a problem. Transform the following LPP into standard form. Okay, here the objective function is already in minimization. So we have to convert, this is in maximization type. So by that is very easy. Maximum of Z star. What is Z star? Z star equal to minus of Z, that is 2x1 minus 3x2. So a simple conversion. So we are going to maximize this objective function. Actually we have to minimize this objective function. Instead of Z we consider Z star. Z star is nothing. Z star means minus Z, right? So that is 2x1 minus 3x2. And what about the constraints? This is x1 minus 3x2 plus 2x3 less than or equal to 3. The right hand side is positive and less than or equal to. So we have to add a slack variable. Okay, so this become x1 minus 3x2 plus 2x3 plus s1 equal to 3. Okay, then what about the second constraint? Here it is less than or equal to, but right hand side is negative. So first you have to make the right hand side is positive by multiplying a minus sign. So this become, okay, so this become minus x1 plus 2x2 greater than or equal to 2. So now the right hand side is positive and it is greater than or equal to type. So we have to subtract something from the left side. Then only this become an equation. Okay, that is called a surplus variable. So we subtract a surplus variable. Yes, so this is minus x1 plus 2x2 minus s2 equal to 2. So this is surplus, this is slack. Okay, Then what about our variables? Here x2 is non-negative, no problem. x3 is also non-negative, that's okay. But x1 is unrestricted in sign. So we have to convert this x1 into difference of two positive variables. So what is the conversion? We have to convert x1 as x1 dash minus x1 double dash. And also we assume that x1 dash comma x1 double dash both are non-negative. So now instead of three variables, now we have four variables, that's all. Okay, so we have to rewrite the entire LPP in terms of x1 dash and x1 double dash instead of x1. Okay. Okay, so our problem is like this: maximum of z star equal to 2x1 minus 3x3, and this is slack variable, and this is a surplus variable, and x1 is unrestricted, and x2. Okay, also we assume that this s1 and s2 are positive. That is true because we add something for making that in equation to equation, and here we subtract a positive quantity to make an equation. Okay, so that's why this s1 and s2 are positive. Now next we have to convert this x1. So we know that x1 is x1 dash minus x1 double dash. So we have two more variables, that is x1 dash and x1 double dash, and we have to convert everything in terms of x1 dash and x1 double dash instead of x1. Okay, so what about our objective function? Objective function is 2 times x1 dash minus x1 double dash minus 3x2, like that. Okay, instead of x1 we have to substitute x1 dash minus x1 double dash. Here also we have to substitute this one, and after the substitution, and you can simplify. So that is the standard form of LPP. So what is that? So standard form is maximization of z star 2 into x1 dash minus x1 double dash minus 3x2, and this one, and x1 dash x1 double dash x2 x3 s1 s2 all are greater than or equal to 0. So this is the standard form of given LPP. This is the standard form of given LPP. Okay. Okay, our aim is to solve a given LPP. So for solving an LPP using simplex method, first we have to convert in standard form. Okay, but we have extra restriction for applying simplex algorithm on a LPP. So this is the another restriction. After converting the standard form, all the constraints, okay, uh, are less than or equal to with positive RHS. That means LPP contains the standard form of LPP. Standard form of LPP contains only slack variables. Then only you can apply the simplex algorithm. Clear? The standard form contains only the slack variables. Then only you can apply simplex algorithm. Clear? So once suppose our standard form satisfies this condition, suppose standard form contains only slack variables, then you can write the first table of the simplex algorithm. Simplex algorithm is an iterative process. So first table is like this. This is the coefficient of basic variable. This is the basic variable, and this is the value of the basic variable, and this is c1, c2, cn. They are the cost from our objective function, and these are the decision variables. These are slack and surplus variable, and this is this a11, a22, etc. from our constraints. Clear? And like that. Okay, for example, this is our problem. Suppose there is only one constraint, because in this constraints we add a surplus variable, so that is not allowed in our simplex algorithm. Suppose this is the maximization type with only one constraint, then it is clear that here the coefficient of s1 and s2 are 0. Oh, sorry, there is no s2, only s1. So here coefficient of s1 is 0 because that is a dummy variable. Okay, we have to we are not interested to involve that dummy variable in our objective function, so we add its cost as 0. Okay, then that's why. Okay, next we have to find the basic variable. What is basic variable? Here actually 1, 2, 3, 4. Now we have 4 variables. Okay, so we substitute n minus m variables as 0. Here m is the number of constraints, n is the number of variables. In this case, n is 4, m is 1. Okay, so 4 minus 1 equal to 3. So we can substitute 3 variables as 0. Normally we substitute the variables we choose. Normally variables are decision variables. That is, we are going to choose x1 equal to 0, x1 double dash equal to 0, and x2 equal to 0. Okay, so if we choose these variables are 0, these variables are 0, then what about S1? S1 is automatically the right hand side. Clear? So that is called a basic solution. That's why S1 equal to B1, S2 equal to B2, etc. Sm equal to Bm. This is the right hand side of the constraint. They are all positive. Okay. So by setting all the decision variables are 0. By setting all the decision variables are 0, we can solve S1, S2, etc. Okay. And what is CB1, CB, etc. CBM? They are the cost. They are the cost of the basic variable. Initially, what is the cost? Initially, the cost of these basic variables are all 0. Okay, then what is this a11, a12, etc., a1n? They are from the constraints. The coefficient of the x1 from the first constraint. This is the coefficient of x2 in the first constraint, etc., like that. Okay, this is the coefficient of x1 in the last constraint, etc. Okay, this is this is simply the coefficient matrix from the constraints. That's all. Okay, after writing this table, we have to evaluate two things. One is Z and other one is ZJs. Okay, Z is evaluating using this formula sigma CBI XBI. CBI is this column, XBI is this column. So first CB1 into B1 plus CB2 into next one plus etc. this one into this one. That is our Z. That is the value of the objective function. That is the present value of the objective function. Next, we have to compute Zj corresponding to every column. How to compute this Z1? This is Z1, second one is Z2, etc. like that. Okay. So how to compute the first one? Using this formula CBI Aij. That is simply, this is our CBI column. Aij means the first column. Okay. And I equal to 1 means first column. I equal to 2 means second column, like that. So CB1 into A11 plus CB2 into A21, etc. This one into this one. That gives Z1. And initially we know that all the CBI is 0. So initially all the ZJs are Zi's are 0. So the Z1, Z2, etc. everything are 0. Okay, once we calculate this Zi's, then next we have to evaluate Cj minus Zj. What is Cj? Cj's are the cost from the objective function. Okay, then this minus Z1. That in this case C1 minus 0, like that. Okay, C2 minus here Z2. That is like that. So similarly, you can evaluate all Cj minus Zj corresponding to every column. Okay. And this Cj minus Zj has some property. Cj minus Zj, okay, and anyway, we have to evaluate Cj minus Zj for non-basic variables, because for the case of basic variable, they are always 0. Okay, because in the case of basic variable, they are always 0. So if you no need to evaluate Cj minus Zj for basic variables. If you evaluate, no problem, that is again 0. Okay. Anyway, we have to evaluate Cj minus Zj for non-basic variables. In the case of basic variable, they are always 0. Then, this is the condition for optimality. After a particular table, if all the Cj minus Zj is less than or equal to 0, if all the Cj minus Zj are less than or equal to 0, then the present solution is optimal. Okay, that is a present solution. Suppose this is not the case. Suppose this is the case. If at least one Ck minus Zk is positive, greater than or equal to 0, and at least one Aik is greater than 0, then further improvement is possible. Okay. Suppose one Ck minus Zk, at least Aik means this is the, okay, okay. Here Aik means they are the elements from the corresponding column, the corresponding this positive column. For example, suppose C1 minus Z1 is positive. Suppose this is positive. Then here Aik stands for the elements from this column. Okay. That means this one is positive and at least one of the elements from this column is also positive. Then further improvement is possible. Okay. Then next step is the variable corresponding to maximum Cj minus Zj such that Cj minus Zj is greater than or equal to 0 will enter the basis. Okay, that means we assume that at least one is positive. Then we have to choose the maximum among such positive quantities. Okay, so that variable will enter the basis. That will be XR, and that is called a key column. For example, suppose these two are positive, and suppose this is 1 and this is some 5. Then among these two, this is the maximum. So we have to choose this, the column corresponding to x2. Column corresponding to x2 will enter the basis, or x2 will enter the basis. Now x2 is a non-basic variable. In next iteration, x2 is a basic variable. Okay, so automatically we have to leave some basic variable from the present situation. In this present situation, S1 to Sm are basic. So we have to remove one basic variable and we have to enter one non-basic variable into basis. Okay, so next we have to identify which one is living variable. Okay, to identify that living variable, we have to evaluate xbi by AIR corresponding to the positive AIR. Okay, then take the minimum. That variable will leave the basis, and we denote that row by key row. That is called a key row. Okay, now XR is our key column. So corresponding to that column, we can construct this XBI by AIR for positive AIR. For example, okay, in this case we choose this is our entering variable x2. Next we have to find the living variable. Suppose the column elements are -1, 2, etc. like that. Okay, so we have to take the ratio using this xbi and this column only for only those positive elements. Okay, so no need to evaluate the ratio corresponding to this a12, because now I am assuming here a12 is -1. Okay, so no need to calculate this ratio. So this is b2. So and now we assume this a22 is 2. So we have to take the ratio corresponding to this, that is b2 by 2. Clear? And similarly, suppose this is positive, then we have to evaluate bm by 5. So you have to evaluate ratio corresponding to only positive entries in this column, the entering column. Okay, then take the minimum. Suppose this is the minimum. That means this basic variable Sm will leave the basis, this will leave the basis, and the present non-basic variable x2 will enter the basis. Okay, so naturally there are some changes in this table. Okay, there is a special case if all the entries in that particular column. Now we choose a entering column. If all the entries in that entering column is less than or equal to 0, then LPP is unbounded. That means there is no solution. Okay, suppose this is the case. We have an entering variable and suppose we have a living variable. Then next we have to identify pivot element. What is pivot element? It is the intersection of key row and key column. Now this is our key row, this is our key column. Then this element is called the pivot element. Okay, in this example, this is our key column, this is our key row. So this entry is the pivot element. Clear? Then to get the next table or next iteration, use elementary row operations to change the pivot element to 1 and all other entries in the entering column to 0. That is our next procedure. That means using elementary row operations, first of all we have to make this pivot element as 1. Okay, so in this case, suppose this row is suppose we have only 3 rows. So first procedure is we have to convert R3 to R3 by 5, because we assume that this entry is 5. So now this element is 1. Next we have to convert every element in this column to 0 using this 1, using elementary row operations, using that like our row reduced forms in echelon forms like that. Okay, and then repeat the process until we get an optimum solution or an indication of unboundedness. Okay, so this is an iterative process. Okay, so this is the algorithm for simplex method. So simplex method is applicable only when the standard form contains only slack variables. Okay, and if number of variables is 2, normally we use graphical method. That is very easy. If number of variables is more than 2 and satisfying all the conditions for algorithm, then you can apply the simplex method. Okay, so in next session we will see a problem of simplex algorithm. Okay, thank you.